A recent scientific discovery has sent shockwaves around the world. The existence of extraterrestrial life may finally have been confirmed. NASA's OSIRIS-RX mission in 2023 returned with DNA-encoded evidence from space that is challenging everything we thought we knew. After decades of searching for signs of life beyond Earth, it now appears that the answer might have been right under our noses all along. Consider this: up to 4% of our DNA comes from Neanderthals, and it's even possible that every one of us carries genetic material from outer space. In other words, we might all be interstellar hybrids. The biochemical reactions that underpin the coding of our DNA might have occurred off-Earth, and perhaps even long before our planet formed. Life, in all its astonishing complexity, may not be an Earthbound accident at all. Discovering that life began so swiftly on our planet offers a tantalizing hint. If life can arise quickly here, similar processes might be common throughout the universe. This could help us gauge just how much we've altered our own environment as we teeter on the edge of self-destruction. Yet, despite numerous efforts, we have only a rudimentary understanding of how life originated on Earth, and our evidence for extraterrestrial life has remained elusive. One compelling hypothesis is panspermia, the idea that life, or at least the precursors of life, did not begin on Earth but was instead delivered here by meteoroids or comets. While panspermia remains a controversial topic with little direct evidence, there is a middle ground, perhaps the essential components of life, the complex organic molecules critical to its formation, originated in space. According to this view, many of the molecules necessary for life did not form in Earth's primordial soup, but in the depths of space, possibly long before our planet even existed. When these substances rained down on the early Earth, they may have jump-started the process that eventually led to the first living cells. The evidence for this scenario is growing more compelling. One of the earliest hints came with the discovery of the Murchison meteorite in 1969, which contained over 90 different amino acids, including several that are rare on Earth, as well as nucleobases, key components of DNA and RNA. Radiometric dating shows that the Murchison meteorite is approximately 4.5 billion years old, suggesting that complex organic reactions occurred in space well before life emerged on Earth. To remove any possibility of contamination from terrestrial sources, scientists have long sought samples directly from space. NASA's OSIRIS-RX mission is a major step in that direction. Launched in 2016, OSIRIS-RX targeted the near-Earth asteroid Bennu, orbited it for several years, and successfully collected samples from its surface. In September 2023, the sample capsule returned to Earth, and after 2 years of painstaking analysis, the first results were announced in January 2025. These findings are nothing short of extraordinary. The Bennu samples contain all 5 nucleobases that serve as the genetic code for DNA and RNA, a first for any single space rock. In addition, they include 14 of the 20 amino acids used by life on Earth. Interestingly, unlike Earth's biosphere where amino acids are predominantly left-handed, the Bennu samples exhibit both left and right-handed forms, suggesting a non-biological origin. Moreover, the samples reveal a surprisingly high concentration of ammonia, 12 times that found in the Murchison meteorite, which implies that Bennu or its precursor material may have formed in a colder, more distant environment. Even more intriguingly, the detection of 11 distinct evaporite minerals indicates that water once played a significant role in shaping the asteroid's composition. The presence of sodium-rich salts, similar to those found in Earth's Searles Lake, further supports the notion that Bennu originated from a water-rich body in the early solar system. Piecing together these clues, one can imagine that roughly 4.5 billion years ago, in the icy outskirts of the early solar system beyond Jupiter's orbit, a distant protoplanet composed of rock, metal, and frozen water began its evolution. Radioactive decay from supernova-born elements melted portions of the ice, forming a nutrient-rich mineral soup. In this environment, water combined with ammonia and formaldehyde to trigger the formation of complex organic molecules. When the water eventually evaporated, it left behind a legacy of saltwater minerals, essentially, the building blocks that may have seeded life on Earth. This growing body of evidence lends significant support to the panspermia hypothesis. While it remains difficult to say definitively how life originated on our planet or elsewhere, the discovery of such rich organic chemistry in space implies that water worlds abound, with ample supplies of amino acids, nucleotides, and other vital molecules. It becomes increasingly hard to imagine that simple life wouldn't emerge in these environments. Observations of nucleobases in extraterrestrial samples might even reveal that all planets began with a similar chemical makeup, hinting at a universal pathway to life. Following its historic sample return, OSIRIS-RX has continued its mission as OSIRIS-APEX, preparing to intercept another potentially hazardous asteroid, Apophis. While this mission is primarily aimed at planetary defense, it also enhances our ability to study near-Earth objects and to further test our theories about the origins of life. Ultimately, These groundbreaking discoveries not only deepen our understanding of prebiotic chemistry and the origins of life on Earth but also hold the promise of answering one of humanity's most profound questions: how likely is it that life exists elsewhere in the universe? As we unlock the secrets of organic chemistry in space, we move ever closer to understanding whether the seeds of life are truly universal. Thank you for watching. Please share your thoughts in the comments, and don't forget to like and subscribe.